We will now be getting a little bit quantitative with enzyme measurements. First of all, we'll be talking about something known as the Vmax and the Michaelis-Menten constant. Michaelis-Menten constant is typically referred to as the Km. More on that in a bit. The idea behind these measurements, now this is going to be I don't want to say complicated. It's not complicated. This has to be chronological. If you're going to follow things along in the exact same fashion that I'm going to teach these things, you will have no problem. If you don't, you will have a problem. Okay. Now, this study is based off of what in the world did I write? How the substrate concentration affects the rate of an enzyme catalyzed reaction. Enzyme catalyzed reaction. It's all about the substrate concentration. It's all about the substrate concentration. Now, in the, I spelled this name wrong, Michaelis-Menten model, it's a model. Okay. Model. Two descriptor values are used. Descriptor values are used. The first descriptor value is going to be the Vmax. Simply the maximum velocity. Maximum rate or velocity of a reaction of a reaction. And then the second factor is the Km, Michaelis-Menten constant. That's why it has a, see, Michaelis-Menten, K means constant. Constant. We'll define these things like this. Vmax here. It's not Umax. I make it seem like Umax. Vmax. What exactly is Vmax? Vmax is exactly the maximum rate or velocity of reaction. There's nothing that's going to be different when it comes to that. Let's copy and paste that exact same thing. That's the Vmax. Defining Km is going to be the interesting part of this study. Follow along when I'm going to be talking about what the Km is. So the Km is specifically the substrate concentration. Okay, keep that in mind. It's the substrate concentration. Substrate concentration at which the enzymes. Now we're adding some enzymes. Now this is the substrate concentration at which the enzymes are working at 1/2 of their maximum rate. 50% of effort. Now if I ask you to run 100 meters with 50% effort, you will not run it with your full effort, right? If it's a 100-meter race and I just tell you, now this is what we typically do in training. This is how we practice things in training. If we have a 100-meter distance, first we will run that distance in a 50% effort. If your best 100-meter time is around, let's just take 10 seconds. It's not easy to get 10 seconds, trust me. 10 seconds, if that's your best at 100% effort, if you take 10 seconds at 50% effort, you should take more time than that. That's the idea. What I'm trying to tell you is, when it comes to the Km, the enzymes are not working at their maximum rate. They are working at half their maximum rate. They're not doing everything that they're capable of doing. They're doing half of what they're capable of. Now, why bother? Why all these measurements and why Km, all that stuff? The reason being, these, I'll call them stuff, these stuff can be used to measure the affinity, hence the efficiency of an enzyme. That's why we need all these things. What is affinity? What is efficiency? We'll talk about that later. What we're trying to do is we're trying to see how effective an enzyme is. If we have enzyme A and enzyme B, let's presume. Say we have enzyme A and then let's presume we have enzyme B. Okay. We want to find out what enzyme is the best. How would we do that? We would have to do some form of quantitative measurement to get a metric value to see whether A is better or B is better or it's the other way around. To fix that, what we're going to do is we're going to be doing the Immobilising model, where we are going to be assessing Vmax and Km to see what the better enzyme is going to be. Now here's how we're going to interpret our results. Of course it's quantitative, hence a graph can be produced. Oops, not an issue. Graph can be produced. On the x-axis, substrate concentration will be plotted. Substrate square bracket, substrate concentration meaning, and of course rate of reaction. Like so. And let's take a simple reaction, okay, like that. It plateaus and stuff. Okay, now let's start with the measurements. The first measurement is obviously going to be the maximum velocity. Now see, this is what we have. That's the maximum the line has gone to. That's the maximum effect of the enzyme. Therefore, we call that the Vmax. Pretty simple, pretty straightforward. That will be your Vmax and your Vmax only. Okay. What about Km? Where do you find Km? If you read through the definition of Km, Km is the substrate concentration. So it's not here. This is the rate of reaction. No, it has to be somewhere here on the x-axis. So Km might be here, Km might be here, it might be here, it might be here. Nobody knows. All we know for sure is it's on the x-axis. Why? Because it's a substrate concentration. We're talking about a substrate concentration. How do we get to Km? Now, from the definition again, we know Km is where enzymes are working at 1/2 of their maximum rate. Now, pay attention to this boxed value. 1/2 of the maximum rate. If I word this in another way, Km is where the substrate concentration lies at which enzymes are working at 1/2 of the maximum velocity. 1/2 of the maximum velocity. Now, if this is the maximum velocity, halfway through this would be the maximum half max, right? If this is the entire thing, halfway through, around here, maybe. So that's going to be the half Vmax. Okay. Now let's follow along. Half Vmax. Now we can obtain what the corresponding x-axis value is. That is going to be your Immobilising constant, Km. Half Vmax, that's going to help us and guide us down towards the Km value. Towards the Km value. Half Vmax to the Km value. That's the idea. It's the idea. Now, how exactly are we going to measure the affinity then? How does affinity help us? This is how it goes. Whenever it comes to the affinity, what do you mean by the affinity? Affinity is simply the effectiveness of the enzyme to hold on to the substrate. The affinity that the substrate has for the enzyme. Affinity is inversely proportional to Km, or you can even say efficiency. Same thing, meaning it's inversely proportional. No? If the Km is too large, it's not a good enzyme. Not enough affinity. We need affinity to be as much as possible. No, affinity is another word for efficiency. If we want a very high efficiency, we're going to need a very low Km value. So for example, if the Km value is around here, that's a good enzyme. If the Km value is around here, that's a bad enzyme, because see, it's a very high Km value. No? High Km value would mean lower affinity. We do not want that at all. The lower the Km, the better. I'll write that final concluding statement here. The lower the Km, the better. That's the idea. That's your study on Vmax and Km. Now, most of the time, this is coupled with inhibition. Examiners love to couple this with inhibition. That's where most students actually go wrong. To make sure that you don't go wrong, this is what we will be doing. I'm going to be talking about an example regarding catalase. It's the same factors. We'll be talking about inhibition and inhibitors and how the Vmax and Michaelis Menten constant come into effect. We'll use catalase as an example. Now what catalase does is, catalase is capable of breaking down hydrogen peroxide. This reaction is completely irrelevant. You don't want that. It's just to give you an idea. Hydrogen peroxide into water and oxygen. If I balance it to 4, 2, 4, yeah, like so. Now oxygen is being produced now, so this oxygen can be collected and measured over time to measure the rate of the reaction of this hydrogen peroxide reaction. Now on top of that, we will be seeing the effect of competitive and non-competitive inhibition on this reaction with respect to the Vmax and Km. It's a simple reaction, a very simple reaction if you will. We'll see how Vmax and Km change if we try to, the first thing, competitively inhibit this, or the second thing, non-competitively inhibit this. Non-competitively inhibit this. I'm going to draw a graph. Okay, let's start with the normal reaction. Okay, that's my normal reaction. So if I was to measure the Vmax of my normal reaction, it would be somewhere over here. And half Vmax is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3, 4.5, somewhere over here. That's my half Vmax for my normal reaction. I'll be color coding all of these things. Green would be everything for my normal reaction, and therefore my Km is going to be somewhere over here for my normal reaction. Not an issue. Not an issue. Same axis labels, okay? Substrate concentration, rate of reaction. Rate of reaction, no speed of reaction, velocity of reaction, same deal. Now let's look at what happens if I add a competitive inhibitor and a non-competitive inhibitor. Now if you recall from the previous spread, the above line is always going to be the competitive inhibitor, the below line is always going to be the non-competitive inhibitor. Now the same analogy applies to this place as well. I think I'll use orange for competitive inhibition and something else for non-competitive. Let's start with competitive inhibition. If you added a competitive inhibitor, this is how the line would look like. Now you don't have to worry, you don't have to draw very specifically. You will not be asked to draw, but you will be provided this graph and you will be asked to evaluate things. So let me draw this. Okay. Green would be for the normal reaction. Orange is going to be for the competitively inhibited reaction. Okay. Now let's assess these quantitative factors. Look at the Vmax. Oh, it's the same as my normal reaction. Now to keep a record of these things, we'll draw a small table. Tiny, teeny little table here. I don't know space. 3, right. First, we'll talk about the Vmax. Then we'll talk about how the Km is going to be affected. Here, competitive inhibition. Here, non-competitive inhibition. Right. So this will be compared to the normal reaction. Okay, this will be compared to the normal reaction. So when comparing the Vmax of competitive inhibition with the normal reaction, it's the same. See, competitive inhibition, the Vmax is going to be the same as the normal reaction. Same as the normal reaction. Same as the normal reaction. But let's look at 1/2 Vmax. Now we have to get Km. No, to get Km, we need half Vmax. So we're going down. Half Vmax will also be at the same place. No, for the competitive one also, that will be half Vmax. So now I'm following through. But you see, it doesn't stop here. Now you have to come all the way here and then go down. Now the Km is that. Orange Km, competitive inhibition. When compared with the Km of the normal reaction, do you see? That is increased. So I'm going to draw an upwards pointing arrow. Competitive inhibition, that's the summary. Vmax is same, guys. Vmax is going to be the same. But the Km is actually increased. Km is actually increased. Let's look at non-competitive inhibition. Now, if I draw non-competitive inhibition, it's going to be a little bit tricky for me to draw it. Yeah, it's going to be a little bit tricky for me to draw. I'll make some adjustments as we go along. This is non-competitive now. That is non-competitive. I'm going to check for Vmax. So it's going to be somewhere over here. That's Vmax for non-competitive inhibition. Now you can clearly see for the original reaction, the Vmax is here. Now Vmax is significantly low. So here, Vmax is low. What about Km? What about Km? Now Vmax is here. Half Vmax for this is going to be around here. No? Half Vmax. Now let's follow through. Something interesting is happening. Vmax is here. Look at only the non-competitive line. Okay, only the non-competitive blue line. Vmax is here. Half Vmax is here. To get Km, I'm gonna have to go to the line and go down. Interesting. Km is now subsiding with the original reaction's Km. So this time the Km is same. Should use blue. I should use blue. Km is the same. Do you see? That's the idea. For competitive inhibition, Vmax is same. For non-competitive inhibition, Km is the same. That's the most important distinguishable factor you have to understand when it comes to dealing with Km and Vmax values for any reaction at any given place. Alright. The last part for this is going to be about how we can immobilize enzymes. The last part for the enzyme spread, 3.4. immobilizing enzymes. What exactly do you mean by immobilizing enzymes? Now, enzymes are usually free. Now, these free enzymes can be fixed or, in other terms, immobilized into inert, insoluble materials such as alginate. There's something known as an alginate bead. Specifically, you can immobilize enzymes onto these alginate beads. Simply speaking, it's a bead. You can have a container full of these beads. Bead, 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 alginate bead, and on the surface of this, you can coat the enzyme, fix the enzyme, or in better terms, immobilize the enzyme. Like so. These are known as alginate beads most of the time. Now, why do we do this? We have some advantages. End product is not contaminated with the enzyme. Meaning, if I put something into here and the products are formed and I filter it out, enzymes will be still immobilized on the alginate beads. Enzymes will not be removed. If I, on the other hand, on the other end of the spectrum, if I put free enzymes, when I take the product out, those free enzymes will also come to me. I don't want that. Here, the end product is not contaminated with the enzymes. Perfect. And the enzyme can be not reused, reused. And when you immobilize these enzymes, they will be better tolerant to pH and temperature changes. They will be more tolerant to pH and temperature changes. That's the idea of immobilizing enzymes. Now, when it comes to a practical usage, I'll tell you something like this. The use of enzymes immobilized in alginate beads to break down lactose in milk by the enzyme lactase. I spelled this wrong. Immobilized. Nope. Immobilized. Here's the idea. It's almost like this little filter funnel that we have. In that, we have alginate beads coated with the enzyme lactase. Like this. Immobilized lactase. Like so. So you put milk in. Lactose is broken down and now you have lactose-free milk. Lactose-free milk. You have lactose-free milk in the container. What have we done? We have immobilized the enzyme. What are the advantages to doing it in this particular fashion, this particular method? We have no contamination. I have spelled enzyme wrong here. We can reuse the enzymes. The end product, the lactose-free milk, is not contaminated with the lactase milk. And these enzymes are going to be more tolerant to pH and temperature changes. With that, we have come to the end of this specific enzymes chapter.